There are three ways in which energy can be stored: sensible, latent, and thermochemical heat storage. Today we are going to focus on sensible heat storage, and in particularly about water. Sensible heat storage is the practice of saving energy by raising the temperature of a material and then taking that heat back as it cools down. There is no phase change and no chemistry involved in the process. Like a battery, it consists of charging, storing, and discharging. During charging, you add heat and the temperature of the storage medium climbs. During storage, insulation limits loss of heat, and during discharge, you move that heat out to where it's needed. The energy you can store equals mass times specific heat capacity times the change in temperature. More mass, a higher heat capacity, or a larger temperature rise all increase the amount of stored energy. This means that increasing yield from sensible heat storage involves either increasing mass of the heated medium, choosing mediums with higher heat capacity, or increasing the temperature of the medium without undergoing a phase change. You can find sensible heat storage in buildings and districts for daily to seasonal use, and in industry whenever there is a useful source of heat to capture. For our project, we will work with water, but everything I have said here applies to any sensible storage medium.
Among storage material, water is one of the favorites because it has a high heat capacity, it is abundant and easy to access almost everywhere and therefore cheap. Finally, it is a non-hazardous medium, non-toxic, non-flammable and chemically stable, making it suitable for various applications, including residential use. It operates safely between 0 and 100 degrees, and pressurized tanks can extend this range, increasing storage density. Being also one of the most ancient and known thermal vectors, systems for heating and storing hot water are simple and mature. The storage is flexible and can be easily scaled from small tanks of just a few liters for domestic use to huge industrial reservoirs.
When we talk about storing heat, one of the simplest and most effective methods is sensible thermal energy storage. To give a quick example, 300-liter water tank heated from 20 to 90 degrees can hold about 24 kilowatt hours of thermal energy. That's enough to cover a big share of a household's daily heating or hot water needs. The most familiar application is in our homes. Hot water tanks provide domestic hot water and buffer heating demand. They can be linked to a boiler, a heat pump, solar connectors on the roof. Modern systems often use stratified charging to preserve efficiency. Now, if we scale this up, we move into district heating. In many parts of Europe, entire neighborhoods or towns use large water tanks or even pit storages. That's basically giant insulated basins dug into the ground. These can store hot heat collected in summer, often from solar thermal fields, and release it in winter. Industry is another important field. Factories often produce waste heat that will otherwise be lost. By storing it in hot water, it can be reused later in the same process or even fed into a local heating system. That improves efficiency and reduces the use of fossil fuels.
Small-scale, low-temperature, sensible thermal energy storage with water is already commercial, while large-scale, high-temperature systems are still under development. One approach is to pressurize the system to allow operation at higher temperatures. Research is also ongoing in seasonal storage using underground reservoirs such as aquifers, boreholes or pits, enabling much larger storage volumes. To be suitable, water-based TES must be powered by renewable sources like solar or wind, which in turn depend on continued advances in the renewable energy. Water as storage material causes problems regarding corrosion and microbial growth, so research on developing more suitable tank materials and water treatment is crucial.